Thanks, Fuguo. Thanks, Yi, for that very impressive keynote. I'm Peidong Yang, a professor of chemistry at UC Berkeley. I'm also the director of Kavli Energy Nanoscience Institute over there. So I will be the moderator for the next 35 minutes. Let me first introduce our panel. Our panel is Professor Brongersma from Stanford, Department of Material Science and Engineering. Professor Liangbing, Yale University, Material Science and Engineering.
Now you get your jacket.
Professor Ting Xu, Professor of Chemistry and Material Science, UC Berkeley. So we live in a materials world. As Fuguo mentioned, materials is really the foundational pillar for human society. For the next 35 minutes, the panel will discuss what will define the material research and technology for the next couple of decades. So we will start with, since the three panelists, including Yi here, their research expertise are very, very diverse, very, very interdisciplinary. We will start with one slide for each of the panelists to introduce their research. Then after that, we will start the discussion. I will start with Mark.
Fantastic. So I think a slide is being pulled up behind me. My field of science and technology is nice and complementary to the one that Professor Yi Cui described. My field is that of nanoscale photonics. We're trying to see whether we can manipulate light at the smallest scales, the scales of molecules and electronic transistors, to make more efficient technologies happening. There are a couple examples here on my slide from left to right, trying to see whether we can harvest solar energy more effectively in thinner solar cells that are less consuming of materials, easier to process at low cost, whether we can manipulate light of solid-state lighting, the light that we have in our building and is illuminating me, see whether we can only control the color spectrum, but also the angular distribution of light to develop new experiences. Displays, making them more efficient for wearables, making them more efficient because often when you wear them on your wrist, power consumption is a very important consideration. We're trying to think about how to use light manipulation at the nanoscale to not only manipulate electrons at that scale, but also photons to make more efficient AI, internet, communication, and computation. How we can manipulate photochemistry, enable new types of sensors that monitor your health, wearables that can provide you information as you walk around. Most recently, we're trying to see, as the transparent mouse shows with my colleague Guo Song Hong, whether we can manipulate light truly at the molecular scale to make tissue of the body transparent, to learn more about the operation of the brain and the organs inside your body. And just to give you one example on the left, so you can have something to think about, on the left bottom is a structure and scanning electron microscopy image that shows the nanostructures that we now use to very efficiently trap light into solar cells that are just a few microns in thickness. So think at least 2 orders of magnitude thinner than current silicon solar cells that we have. That would allow things to be flexible, lightweight, fly on drones, planes, more easily give you energy in your watch. And truly, if you see that one can find out what the best ways to enhance efficiency are, is to use nanostructures that are highly engineered using many different computational techniques. And maybe during the panel we can discuss some of these approaches. Thank you.
Thanks, Mark. Liangbing.
I'm Liangbing. I'm a professor at Yale University. So I run a very cool material kitchen at Yale. So we focus on materials innovations. And my group right now focuses on 3 major research areas. So the first one is about the furnaces, high temperature furnaces. Whenever you make materials, the most important parameter maybe is the temperature. Right? So in this high temperature community, there are a lot of issues in developing high temperature furnaces. So since I became an independent professor at Maryland, now I'm at Yale, I actually been working on ultra high temperature furnaces. With this kind of a furnace capability, we were able to invent and manufacture a broad range of ceramics and metals, including catalysts, solid-state battery membranes, and even from plastic to jet fuels, for example. So, for example, here we invent a process called ultra high temperature plasma, and that actually has a temperature that is higher than the surface of the sun. So that actually really enables us to discover a very broad range of new materials. The second topic is about engineered wood. We call it wood nanotechnologies because we study wood at the nanoscale. So when you convert wood at the nanoscale, you can invent a very broad range of new materials. One example is something called superwood. It's 100% wood, but it has a strength even higher than steel, but 6 times of the density. Right? So, and I think this will actually help address a lot of sustainability issues in the long term. The third topic is about batteries. As Yi mentioned, I did actually postdoc with Yi, but I focused on solid-state batteries using very unique high-temperature process to synthesize solid-state ceramic membranes or using wood fibers for solid-state paper fiber-based batteries. So in summary, my group works on heaters, wood, and batteries. Thank you.
Thank you, Liangbing. We will have time to talk about manufacturing a little bit later. Now, Ting.
All right, so I am the polymer person here, and I would say genetically, we are all starting from a piece of macromolecule. So for whatever worse, I just wanted to give a quick recapture of history. Among all the different disciplines, polymers is the youngest. If anything, it's really the taller in the room when you talk about material science. Since 1920, when the micromolecule concept has been introduced, the field start to realize that we can really use this long chain putting different things together. And historically, the field actually diverged. You have a bio community, we study DNA, we study protein, we study how they function, make us better, as you may see from the earlier session. And in parallel, the industrialization made us to make polymers without even consider what is the consequences. We actually see that sort of gave polymer a really bad reputation, but I do want you to keep in mind that in essence, we're all made of polymers. We function. If polymer fails, we are not going to be out of here. So I think there are 3 areas that the current field is pursuing. One is that we wanted to transition from a commodity to high profit margin, high functional materials. You can see quite a bit of effort in there. In parallel, we do have this pile of trash, as well as all the new plastic we're going to make, how to engineer circularity. And the last, and perhaps not the least, is what I'm most excited. What I think the new era for polymeric materials are really looking at how to do information embedding and really taking the result that we achieved through evolution to embed it into the plastic so that every piece of polymer we made can behave like what we have that support our life. So I think that's where the future goes. Yeah.
Thanks, Ting. So as you can see, our panel here basically touched upon from the hard matter to soft matter, various energy technology, very diverse. Again, material science, material research is very, very interdisciplinary efforts. So I will start with the first discussion. Nowadays, everybody is talking about AI, okay? The materials discovery, large data set, and inverse design. It seems it's starting to impact every aspect of the material design and the synthesis in the research lab. So my first question to the panel is, in the last couple of years, how you see in your lab that AI is impacting your research? Is that AI is just helping you doing experiment faster, or there are much more significant things behind it? Since Yi hadn't touched upon the AI efforts in his keynote, I will start with Yi.
Thank you, Peidong. AI, very important for materials research. I started to try AI for materials about 10 years ago. But let me share with you first, the thinking is, hey, AI for science, what's the most successful example nowadays? Can we learn from that for the material science? The most successful one is our AlphaFold. I touched upon the previous panel. How do you use AI for protein design? The reason it's successful, you have protein data bank, very good data. You have the AlphaFold, you have the algorithm, nicely designed, then you have computing power. And these three things are important. Now let's look at materials. 10 years ago, I was suspicious about AI for materials. Then I hired a graduate student, a PhD, to work on it, to see whether that's real or it's not that much. So we've tried to predict solid state ion conductor. And the first success, I was surprised. It actually identified materials, new one, looks promising, but only promising at this moment. We cannot claim the victory yet, right? And then we have further tried recently in our organic electrolyte for the lithium metal batteries, start to identify the new molecules that actually work quite well, but not to the level can claim the victory. I would say, well, my prediction is AI will be so important for material science research, but whether we can get to the level of like designing protein, predicting the protein, we need much cleaner data for material science. We probably need material-specific algorithm to do with that. And then we need high-throughput experimental tool, the robots, to do the experiment. It got to get these three things. Computing power, we probably need quite a bit. So I think we need these four things right there. Yeah.
Yeah, I agree. I think using AI for structural prediction is the first step. Going towards function is much more challenging. Ting, you want to add something?
Thanks. I thought I'm going to be the last one. So it depends. All right. So I can go from the most negative to positive, or most optimistic to most to the past. So let's start with the optimistic, and given how positive he is. So for the last part, which I'm particularly excited about, is to look at information encoded plastic design. That's where we design plastic from the get-go that allow us to really take advantage of evolution results. Now we can call it AI. 20-something years ago when I was postdoc, that is called de novo protein design. And some of you probably know Dave Baker won the Nobel Prize for, back then, we know he did Rosetta. So in that front, I think it's great because we have a large library of database from the bioinformatics. And then that coupled with physical chemical science, for example, if you think about ab initio, DFT, atomistic MD, coarse grain, Monte Carlo, I think if you can do that, I think it's going to help us design materials. I think that's where the future, and I think it's going to be very transformative. But now I'm going to shift to the other end. Polymers never really give you things in deep energy well. Okay, you can find a phase diagram for a very simple component. You do a binary blends, you're going to get a well-defined phase diagram, but kinetic pathway, oftentimes is really difficult to get into it. But when you really start to think about that, biology, or if you think about the commercial product, they are never pure binary component. It's always this multi-component. Complexity, heterogeneity is a hallmark in biology. That's the ultimate of soft matter. And in fact, look at every product you bought from the store, they're never binary. So what that means that you have to deal with this complex free energy landscape. And what it means that you don't have a data to learn. Polymer is not governed by equilibrium. It's governed by non-equilibrium state. So I will, given the power of the computation right now, given the lack of a data we have, and given the fact that data out there are all biased. My group, we do things, the prediction power is 80% right. That means that the human intelligence is already there, and that biases data. So I think the challenge for the field, or maybe a petition from us to the field is that can we do this convoluted human intelligence coupled with AI and using the data that is already biased? I think that's where AI can boost the field, at least in the soft matter.
That's great. Mark?
Great. Yeah. So let me start by saying that light will be at the foundation of all of the AI technologies. If you look at the exponential scaling with which we use more computers to process information and send information around the globe, it's clear that we currently don't have really good solutions to power those AI systems. Data centers already consume something like 5 to 10% of our global energy consumption. People are frantically searching for ways to power AI 10 years from now. It's very clear that electronics will keep playing a major role in that, but that photons that can transport energy and potentially can help with some pre-processing of information is going to play a major role. So that's on the usage of photon side. And then the next question, okay, how we're going to design such photonic elements that will help power the age of AI. And this is where the simple realization is that we've moved away from conventional optical elements where we used glass lenses to focus light and mirrors to redirect light beams. Such structures are no longer able to manipulate truly light at the scale that we need, the scale at which we move electrons around on chips. There, the only way to design these structures is also to help have AI help us design. In our case, we have the advantage over the people doing batteries and polymer science and make materials that we solve Maxwell's equations rather than Schrödinger equation, for which there are exact solutions if you have the optical properties, the refractive index of the material. So we can generate a lot of data ourselves. We also will need to generate lots of data through experimentation. And together you can see that AI is helping us design structures that human intuition would never have come up with and that are already more efficient in many ways than the tools and designs that we came up with. So it's going to have a big impact.
Yeah. Liangbing?
I think given what has been said, I just want to add 2 points here. I think talking about AI, we have to think about the closed loop approach. Means that experimentation, rapid experimental synthesis and co-organizations will be super important. So AI will give the prediction, then you will have to actually make the material and feed the data back to the prediction, and then you close the loop. So Peidong asked, our own lab experience. So we work on ultra-fast synthesis. One of the major motivation is not only trying to manufacture material at the high speed, but actually trying to accelerate the material discovery. So for example, when you make solid-state battery ceramics, typically it takes about 10, 20 hours here. But in our process, we develop, toward this goal, is something called ultra-fast synthesis. We can make the membrane in about 10 seconds. And it's not just the speed, but also the quality. You can avoid a lot of issues during this slow synthesis approach. So I would just want to emphasize rapid synthesis is going to be very important with the precision control. So that is the closed loop aspect. I think the second part is we have to be realistic about AI, right? So, and a lot of amazing discoveries or innovations actually happened because of defects, because of failures, because of something strange happening in the lab. So I want to emphasize, actually, I personally believe AI will never replace people completely. It will help us, but we have to be there to see what is really going on and actually jump out of this AI prediction. Maybe you have to open a new research hypothesis and then use AI as a tool. AI will help accelerate our process a lot, but simply rely on AI and completely, I think that can be a danger actually. We just rely on AI, right? And we forget about the fundamental science, fundamental, logic thinking, that can be very dangerous. Yeah. I just want to add that.
Yeah. Peidong, can I resonate with Liangbing? So you look at AI, it's actually, I would say, reasonably successful in molecular system. But when you go to solid state, the problem being mentioned start to show up. Your defect, point defect, dislocation, stacking for this, your data doesn't capture. You cannot learn. And the variety is so big. That's why solid state is so hard. Molecular have a defined molecular structure right there. It's fixed, the number of atoms. Small molecule, that's why success starts from small and go big, go to solid state. Solid state might be the hardest one. I just want to resonate
again,
with that.
I mean, structural part is relatively first step.
Yeah.
When it comes to the function, it's always about not just the structure, it's the defects, all these different morphology, different sort of aspect of materials design. Okay, I want to follow up. Let's say imagine in 10, 20 years, in each of your lab, will there be more robots or more graduate students?
I don't want to make my graduate student nervous.
If so, whether your answer is yes or no, could you offer some advice to the current graduate student?
I have 35, 40 students and postdocs in my lab right now. Given the funding situation, very likely to shrink. So my prediction will be if probably robot, one student, one robot, one-to-one match for a while, for next 10 years, and later maybe more robot than student. That's my prediction.
I really agree with what you said. I think we're going to see more robots, right? And given the funding situation, and also robots can do a lot of work. I think the grad student number will decrease. At one point, robot may do most of the work. But I think that will be a good thing, and that means we can do a lot of thinking. We can avoid doing a lot of routine work, and we have high quality data. And then grad students need to be more challenging, intellectually more challenging work here, and to speed up all this discovery and manufacturing. Yeah. I think that will be a good thing, and I think I'm very excited for that. Yeah.
Mark?
Yeah, maybe I agree that robots will start playing a role. I think the form of a robot can take many different shapes to help quicker experimental data gathering. This is something that AIs obviously can't really do if you think about how they interact with data. A lot of data comes in through the eye in the form of light, and that data stream is unparalleled. So equally, I think the quality of our students is, in terms of creativity, is unparalleled. And it should not be underestimated how communities like this and communities of students are never, in my mind, going to be replaced, as they act as emergent systems that can produce ideas that AI thus far, I think, is not able to produce. So maybe the professors will be replaced by robots, but I think the students will have a long time to go. We'll have to look for our accelerated retirement plans.
I think having more robots is not avoidable. I think what happened is that students probably will have to do more soul searching. And I wanted to give you one data point to validate that proposal. So like many others, we love to do science. We love to stay in the lab. But I think one thing, the silver lining brought by COVID, that completely changed the way how we do research, was the fact that students cannot access lab. So then what happened is that we realized that you can draw the same conclusion without getting more data. The only thing you have to do is you have to look at your data harder. So as the data getting more and more, and as we are going to be replaced by robots without any doubt, and I think the future generation for graduate student is really to train deep thinker instead of hard worker.
Yeah, maybe very quickly. I think the number matters, but the relationship between robot and student also matters. So student owns the robot doing more work. I predict that will be the case. And also Mark, your robot, I probably can co-advise your robot as well, right? I think the collaboration nature also changed, right? Peidong cross Stanford Berkeley collaboration. Can I talk to your robot?
But keep it in mind, I do want to warn people that you can be flooded by data. And if you are now thinking, you let the data, you let the robot take over, you may miss the most important. Throughout my career, I say my most important discovery is always by chance. It was because my personal experience, the fact that I had my son, the fact that I spent some time with him, the fact that one day I was taking a walk, just a tree fall off, and not a tree fall off from sky, a leaf fall off sky, something like that. Yeah. So I think this science, I think we are really lucky. Science, a lot is driven by chance.
Yeah, maybe I can add, I completely agree. I think if we only rely on robot or AI, I think we could be very superficial. And I agree. Like for example, I talk about the superboard a lot. Actually, the discovery was that at one point the student drop a sample to the floor. I don't think the robot will be able to recognize that and then tell you, oh, there's something amazing going on. Right? So, because the robot will do the routine things, right? A lot of major discoveries happened at the defect level. Even sometimes you fail the experiment, but something amazing happened. Yeah, and I think it happened again and again. We heard about these kind of things again and again as well. Yeah, so I think. I think robot help us, but we have to be even more challenged, actually more intellectually upgraded to do a better job.
Yeah, I hope the robot will not take away our capability of critical thinking. So I think there are reminders actually getting on to the Q&A. Oh, I prepared lots of questions. I think I want to actually spend 2 minutes just for the panel to discuss a little bit more on the sustainability part of material research. As all of you know, material research, whenever you have materials discovery, you always have a good things associated with it, sometimes with also unexpected sort of consequence. I take plastic as an example. When it was invented, people think that's a materials miracle. But nowadays, microplastic, PFAS is everywhere. It's a disaster for the environment. So very quickly, I want to the panelists to talk about how can we, in the future, design materials in a more sustainable way so that it minimize the potential environmental impact of materials whenever it's large-scale produced. Ting?
Thank you. I appreciate that. How the plastic has to be on the frontier. So there are a couple of things. To connect the last question, I do think AI is going to be instrumental for sustainability. The reason is that not because it is just for the science, for the next generation material development, but rather because it's interdisciplinary in nature. So we had the fortune to work on the topic. Plastic, think about it as a poster child. What it's really come down to is that scientists, engineers are only a small part of the equation. You have to work with people who are dealing with environment, dealing with ecology, dealing with waste management, dealing with business school logistic chain, dealing with policymaker, dealing with consumer behavior, dealing with the general public, how the geopolitical change, all the things in there. I think that's where AI, data science can really help to guide us to think about next generation material design. You can probably tell by now how much I bank my buck on the learning from evolution results and then using what nature already told us through many years of results to develop future materials, really at the system level. And I think we are probably in the golden age, given what happened in the last few decades, in the nanoscience, in the molecular insight we have, in the ability to manipulate almost like each one atom at a time, in your case, probably each phonon, each photon. And I think we are really in the golden, probably one of the best time one can ever imagine to change the way how we live forever. Keep it in mind, we're not doing it for just for the heck of it doing science. We're doing it for ourselves. It is really a selfish quest that we all have to fulfill.
Okay, I think we are running out of time, so I will not ask for further perspective on that, that topic. Now we are open to the audience for questions. Oh.
Okay, can we go?
Yeah, you go ahead. You go ahead.
Thanks. So first, I'm also a polymer scientist by training. So big shout out for Professor Xu for recognizing polymers on stage. So I think all the professors commented a lot about what AI can do for material science. Maybe can some of you also talk about what material science can do for AI? Maybe something we don't already know. Thanks.
Mark, you want to talk about your optical photonics?
Yeah, I think it's nice when you build new materials that you learn that sometimes human intuition is not sufficient, and you start to talk to AIs and programs to design new materials. In our case, we are designing a class of materials that are called meta materials. These are materials that are structured below the wavelength of light. We have slowly over the last 2 decades built better computational programs. But AI has really given us a new wave of insights in how to design such materials where the properties are more given by the size and the shape and the arrangement of nanostructures than maybe the materials that are built up from. And that has also is linking now into sustainability. We can select more earth abundant, for example, materials, non-toxic materials to design new structures. So by doing materials development, we learn that has helped us design new computational techniques that now again make us or enable us to make better materials. I hope that answers your question in part.
Okay. One more question over there.
Sure. Thank you for the discussion. My name is Avlash. I just finished my freshman year undergrad at Columbia. As a young person concerned about the climate crisis, I want to focus my question on the challenge of commercialization. Mark, you mentioned your lab researches nanophotonics, light harvesting, and flexible solar cell applications. Fellow panelist, Professor Yi Chui, has had some success in translating several material innovations.
Can you ask your question? Because we are running out of time, so please. Yeah.
Into companies. So my question is, given some of the challenges with silicon, like low-cost silicon manufacturing, do you foresee the bottleneck in the energy transition being technological innovation or manufacturing policy and capital?
It's all. Everything needs to come together. That will be my answer.
Yeah, the supply lines are extremely important, but thinking about innovative science to more effectively make use of your materials is going to be equally important. Yeah, organizing the politics, supply lines, incredibly important. Maybe in part why we are here.
Okay, as a session chair, I was told we had to stop this panel discussion.
Yeah, so
it's very popular.
Section.
I can see that. Unfortunately, really run out of time. Maybe,
let's thank the keynote speaker and our panelists for the wonderful discussion.